Any questions from the exam? Any problems you want to see worked out real quick? Yep. Right. Say whether they're exact. Absolutely. So I would say this is where probably the majority of points were lost on the exam. You know, it's always a balance when you're writing an exam. For instance, one question would be, how was the time for exam? Did you feel like you had enough time? That's good, but the trade-off for that is have fewer problems on there, which means each problem is worth more points. That's always the balance we end up fighting when you're writing an exam. So for instance, this one, it was 3 points for each problem for determining whether it was exact or not exact. And then it's like the other separation of variables, the other techniques, it's 8 points for the solution technique, which means, you know, not exactly ideally, but if you wrote down not exact for the one that was exact, that basically cost you 11 points, which is a pretty big chunk for that problem, right? That's the trade-off once again with time. All right, so we had 2 of them on there. We had this one. Oops. And the other one was x squared minus y squared dx plus x squared minus 2xy dy equals 0. Remember, the whole theory behind this guy is we are looking at a differential of f, and the definition from Calc 3 of a differential would look something like this. And we're basically looking for a certain function. If my function is equal to constant, my differential would be 0, and that would match up with some derivative or differential equation we're working with. So this f sub x piece is paired with the dx. The f sub y piece is paired with the dy. If you divide it through by dx, you could write this alternative form. Okay? This is what I'm hoping is f sub x and f sub y. Same thing here. This should be my f sub x, f sub y. If there exists that capital F, I'm hoping those are those extra pieces. To check, I'm going to calculate the mixed partials. So if this piece is f sub x, I'm going to calculate that guy, which means taking the partial of this piece with respect to y. I would get 0. I would take the partial of this one with respect to x. I would also get 0. So this one is exact. Over here, I would calculate the partial derivative of that first piece with respect to y. I would get negative 2y. I would take the partial of this next piece with respect to x, and I would get 2x minus 2y. So not exact. Do you want to see the solution process too? Sure. 2 ways to do this. There's kind of like the quick cheater method, I'll call it, right? And then there's the more formal process. The quick and dirty method, I'm still looking for a counterexample to, is to basically integrate this one with respect to x, this one with respect to y, and eliminate any double counted terms. So if we're really doing it that way, I'm integrating the first piece with respect to x. I get x squared minus x. I integrate the other piece over here. I get 3 halves y squared plus 7y. There are no common terms here. Really go like that. The more formal process is to say, okay, f sub x is equal to 2x minus 1. Integrate both sides with respect to x. I get f is equal to x squared minus x plus my psi of y. Calculate the partial of that guy with respect to y, and I'll be left with just psi prime. I can then compare this f sub y with this f sub y. I get psi prime is equal to 3y plus 7, which means psi would be equal to 3 halves y squared plus 7y. So my f then would be x squared minus x plus that psi of y, 3 halves y squared plus 7y. And my solution is not that. My solution is that thing equals constant. Other questions? Yep. And show me after class, and I'll look at it. Because absolutely, if you multiply this by -1, it should still be absolutely counted correct. Yep. Other questions? I'll also post the key later today or tomorrow early. You can look through it over break and bring any questions you have about the scoring to my office during office hours or whenever you get a chance. Okay. Question over here? Any other questions? All right. All right, the topic for today then is to move on to section 2.5, talking about inhomogeneous differential equations. All right. So in this section of the text, I'm going to add a little bit of notation to kind of help give us a little more structure to the section. I'm going to follow what they do in the text, but changing the notation a little bit so we have some kind of tools we can reference. Okay. Once again, make sure your phones are away off the desk so we're not distracting. Okay. So the idea is we have this nth order linear differential equation, and it's not homogeneous anymore because we have this f of t piece. Now we've already seen that if we have a linear differential equation, that we can use the operator notation to represent the equation now. Right? If I defined my L here to be the action of all these derivatives on the left-hand side as the differential operator, then I can rewrite the whole equation as L of x equals f of t. Right? So in other words, that would be like L would be something like a sub n, the nth derivative, plus a sub n minus 1, the n minus 1 derivative. All this stuff is a big operator being applied to x. Okay. So how are we going to solve this inhomogeneous problem where we do have this right-hand side that's non-zero? Well, the first thing we're going to do, instead of just working with this one, is we're going to solve this equation. This is a different equation. This is the associated homogeneous equation. Okay. So I'm basically going to pretend that right-hand side is 0 and solve that equation. Okay. Now, what do I mean by that? I'm going to find some x sub c. This will be new notation here, which I'm going to call the complementary solution. It's the solution to the associated homogeneous problem. And what does that mean that it's a solution to that problem? It means if I take my operator here, that left-hand side, all those derivatives, and I plug in my complementary solution, take all those derivatives, plug it in the left-hand side, the right-hand side should end up to be 0. It's going to kick out a 0 when I plug in this solution. Okay. Then I need to find one solution to the inhomogeneous problem. Okay. I need to find what I'm going to call x sub p. This is going to be my particular solution. And once again, the idea here is if I plug that value in, I should get that right-hand side as the output. And you might ask yourself, well, wait a second, aren't I trying to solve this problem? I'm going to use this xp. Isn't that the solution? Can I just be done with xp? And the idea is no, because this xp is just one specific solution. If we think of what x sub c looks like, we've looked at that before. We've looked at solutions that look like c1 e to the t and c2 e to the 3t, or all kinds of variations there. That is a family of solutions, infinitely many solutions, where because c1 and c2 could be any constant here. This x sub p that I'm talking about, that's going to be one specific solution. xp is going to look something like t squared plus 4. I don't know. No constants there, not a big family of stuff. It's one specific solution. Okay? And the idea is if we know that one specific solution and we can find our general solution of the homogeneous problem, we can then form our general solution. Our general solution to the non-homogeneous problem is just going to be x sub c plus x sub p. We're going to pair those two guys together. Okay, so this is going to be our general solution. And one question is, is that even a solution? I know if I take two solutions to a linear homogeneous system, I can combine them and everything is wonderful. It's going to be another solution. But here I'm comparing one solution to the non-homogeneous and one solution to the homogeneous. Is it okay for me to put those together? Is it still going to give me a solution? To show that it is a solution, we're just going to use the property of linearity. So how do I check to see if this is a solution? Take all the derivatives, plug it in. Notationally, I can write that as plugging in this thing into my operator, x sub p. And I'm hoping that in the end, I get f of t. If I can plug in x sub c plus x sub p, and the output is f of t, it is a solution. Okay? But without actually taking those derivatives and doing all that work, because it's a linear differential equation, it can be represented as this linear operator, I know that it has the property that L of x sub c plus x sub p is the same thing as this, because it's linear. But if x sub c is the solution to the homogeneous problem, then L of x sub c is what? 0. That guy is just 0. If x sub p is one solution to the non-homogeneous differential equation, then L of x sub p is what? F of t. And then 0 plus f of t is just f of t. It's like when we add solutions to the homogeneous problem, they don't really affect the outcome. We plug them in, we take out the derivatives, they eventually go away. Right? So really we can take any solution to the non-homogeneous and include the solution to the homogeneous problem. Any questions there? All right, no, that's very exciting, very notational. So let's kind of go a little more specific here, so we can really see what this feels like. All right, step 1 here. I am telling you x sub p is 2t minus 3. But is it really? Is that really a solution to this differential equation? Go ahead and verify that. Take the derivatives, plug it in, see if you get a true statement into this non-homogeneous problem. Do that very quickly. You want to move on to the next step? Go for it. All right, into the solution. What is the derivative of x sub p? 2. What is the second derivative? 0. Wonderful. Plug that guy in. We get 0 plus 3 times 2 apparently, plus 2 times x, which is 2t minus 3. Plug that guy in. Now I'm going to do those calculations. I get 6 plus 4t minus 6, which is equal to 4t. Perfect. All right, that's what I wanted to get. I got that right-hand side. It is a solution. What about 2xp? Is that a solution? Let's check. 2xp would be, it would be 4t minus 6, right? All right, we're going to call that guy xp2. I don't know. Very creative, right? All right, what is xp2 prime? That'd be 4. xp2 double prime, 0. 0 plus 3 times xp, that's going to be 12, plus 2 times this guy is going to be 2 times 4t minus 6. That's going to be 12 plus 8t minus 12. That's 8t. Is 2 times xp a solution? Is not a solution. That seems strange, right? Can I multiply my solutions to get solutions? Not for the inhomogeneous problem. We were talking about solutions to the homogeneous problem. Form a vector space. I bring in linear algebra. Right? They form a vector space. That says you can't add any way out of space, you can't multiply any way out of space. So you can add these solutions together, you're going to get a solution. You can multiply by scalars, you're going to get a solution. That's all true for homogeneous differential equations here, not for the inhomogeneous. If I double my input, double my output here, right? And because that right-hand side is not 0, they don't line up anymore. Okay? All right. Get rid of that guy. Complementary solution. All right. We've done that before, right? Now we're basically solving x double prime plus 3x prime plus 2x equals 0. We generate our auxiliary equation, r squared plus 3r plus 2 equals 0. We factor that guy. I get r plus 2, r plus 1. So r must be equal to -2 and -1. Looks like my complementary solution should be some constant e to the -2t, some constant e to the -t. Now I form my general solution. It should just be xc plus xp. It should be c1 e to the -2t plus c2 e to the -t plus 2t minus 3. That is the general solution to this non-homogeneous problem. And once again, we showed why that worked kind of symbolically. We're doing the property of linearity. But just real quick, let me demonstrate that right here, right? If I choose C1 to be 0 and I choose C2 to be 1, I would get a solution that looks like e to the -t plus 2t minus 3. Okay? Is this a solution to the non-homogeneous differential equation? It is, right? I have my general solution, that's solution for any values of C1 and C2. I've chosen specific values of C1 and C2. This should be a solution. Let's verify. X prime is -e to the -t plus 2. X double prime is +e to the -t plus 0. Plug all that guy in. E to the -t plus 3 times -e to the -t plus 2. Plus 2 times e to the -t plus 2t minus 3 equals 0. Now I could just expand this and show that it works. But what I'm going to do instead is kind of rearrange it in a special way. I'm going to say e to the -t plus 3 minus 3 e to the -t, that's this piece, plus 2 e to the -t, that's this piece. Those are all the pieces associated with this extra part. Okay? And now I'll group the other pieces. The other pieces are 3 times 2 plus 2 times 2t minus 3. And the question is that equal to 0? This is just the same thing I had when I verified my original XP. This is all the spot that was associated with that extra piece from the complementary solution. But if I just add up this stuff right here, it's going to be 0. It has to be 0. That's part of the complementary solution. If I plug it in, take the derivative, it's supposed to be 0. And so it does. So I just want you to kind of see how it breaks down, where that complementary piece, how it's really affecting the solution. Any questions there? Okay, this stuff right here, concepts, right? The big picture. This stuff right here, those are the steps. Yep. Which X? This one? This one right here? I chose a value of C1 and C2. I just wanted to see if I could pick one and actually show there was a solution, right? I showed that just this piece was, but I wasn't sure if I add one of these pieces, will it still be a solution? So I chose C1 to be 0 and C2 to be 1, and that kind of gave me this extra little piece here. Yep, that should be a solution for any value of C1 and C2. Like if we had initial conditions, that would tell us exactly which C1 and C2 to choose. In general, I can choose any one I want, though, and it still should satisfy the different. Good questions. Other questions? Yep. Right, so this side was 0, but this side over here will give me that 4t piece. All right, yep, sorry, you're right. Thank you. Yes, make sure you change your notes there. Thank you. Other questions or comments? Okay. All right. The big idea, though, is that we form our general solution by taking xc plus xp. There's only one problem. What's the problem with this process? Well, I gave you xp, right? That's kind of the important part, right? So really the question for solving non-homogeneous problems is, how do we find xp? That's really the game here. You know how to find xc. Now you know the general solution is xc plus xp. How do we find xp? We're going to learn two techniques for finding xp. The first one is variation of parameters. Sometimes they're abbreviated as VOP. And the other method is undetermined coefficients. First one we'll talk about is variation of parameters. This is a very general approach. It will work with most differential equations. There's not going to be any restrictions on it. It's a little bit hard. It's a little challenging to get through it. But it's very versatile, very powerful. Undetermined coefficients can only be used in some certain situations. Right? With that f of t on the right-hand side, when that's ugly, we can't use undetermined coefficients. We have to use variation of parameters. But when you do have a nice f of t, kind of a more basic problem, then it's very easy to go through quickly undetermined coefficients. That's kind of why we're going to show you the two different techniques. We'll start with variation of parameters. All right. All right, so here's what we're going to do. We're going to go through kind of a general process of variation of parameters. You do not need to write this stuff down, and this is how I'm going to solve this problem. As we go through it, we're going to see the important pieces and kind of give us a little mechanical process, right? So I'm going to start by saying, we're going to make this assumption, and then we're going to plug it in, and we're going to see this and this, blah, 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 blah. And then in the end, we're going to establish a mechanical process to calculate this thing, this thing, this thing, and put them together like this. Okay? So it's going to be kind of a theoretical approach, and then we're going to really go through a mechanical process that you need to do your homework. Okay? All right, the idea is this. We're going to try to find this general approach by starting with a general differential equation. We'll start with second order, keep the computations down. P and Q here can be any function of x, or any function of t, any function of the independent variable. We're given this guy. Notice an important piece here. What's the coefficient to the leading derivative? 1. Okay. Does that mean we can only use this in the case where the leading coefficient is 1? Pretty much. But you can take any differential equation, just divide through by that first part, and make it 1, right? So if you get something with a 3t here, divide through by 3t, right? Put it in this form. Okay. But understand when you divide through, that will change your values for P and Q and F of T. And so this, going forward here, is kind of starting with this form. All right, when you have this guy, you can find this piece. That's the solution of the associated homogeneous equation. You can find the complementary solution, right? We just kind of ignore F of T and then do our auxiliary equation stuff and find our complementary solution. So we can do that, which means we can figure out what x1 is and x2 are. We've done that before. But now we got to find our xp. And so my question would be, could xp equal 2 times x1? Would that be possible? Why not? Yep. Right. So when I plug that into my differential equation to check to see if it works, what am I going to get? 0, right? So it's not going to give me f of t. It's going to give me 0. It's part of the complementary solution. Okay. Doesn't matter if it's times 2, times 3. So I cannot use any number times x1. What about x2? Can I use some number times x2? No, same argument. So I can't use some number times x1 and some number times x2. So what am I going to do instead? I'm going to try to figure out some function times x1 plus some function times x2. We talked about this kind of idea earlier when we were talking about reduction of order. And now we're going to use it more powerfully, more generally in variation of parameters. So I am going to assume that xp looks like some function times x1 plus some function times x2. Thus, I can form my solution as soon as I can figure out what k1 and k2 are. So I have a new mission. Find k1 and k2. Once I have k1 and k2, boom, I'm done. Okay. All right. If this is a solution, if it looks like this, I should be able to take the derivatives, plug it in, and get a true statement. And that's what I'm going to do. I'm going to plug it in. That's what I get when I plug it in. Good times, right? So you got product rule, and then a couple of product rules, and more product rules. Gets really ugly. And then we use this special operator. Let me know what that operator is. Magic algebra wand, right? Lots of algebra, some other simplifications. And we simplify to this. Okay? There is a lot of algebra, but there's also some other simplifications. Like when I write this out, look at this little piece right there. Look at that little piece right there. I know what that value is. I can assign a number value to that. What number would I assign to that? What? Close. That looks like the left-hand side of the differential equation, right? But if I plug x1 into that left-hand side, what do I get? 0, because x1 is a solution to the homogeneous problem. So I can recognize that as having to be 0. I can recognize this as having to be 0. Those pieces go away, algebra wand, I get left with this guy, right? Well, that really helps. All right, I get this guy. Now I'm looking at this guy and saying, okay, this is supposed to somehow equal that f of t. All this weird junk on the left. What needs to happen for that piece to equal f of t? I'm going to make an assumption and then see what I need to happen. If I assume that x1 k1 prime plus x2 k2 prime is equal to 0. If that's equal to 0, then this term goes away. What about the next term? Goes away. Good assumption. Okay. If I make that assumption, I still need this to be equal to this. I need x1 prime k1 prime plus x2 prime k2 prime to equal f of t. By making that assumption, I simplify everything down to a 2 by 2 system. Now all I have to do is solve this 2 by 2 system for k1 prime and k2 prime. In fact, actually, I can take that system and rewrite it like this. a little matrix notation. Okay. All right, now I need to solve that guy. Well, there's a couple of different ways to solve this matrix equation. How can I solve this matrix equation? What could I do? I could row reduce, absolutely. I could write a augmented matrix and do row reduction. I can definitely do that to solve it, but I kind of want to have a general process here. What else could I do? I could also calculate the inverse matrix, multiply both sides by the inverse matrix. Now for a 2 by 2, I have a little formula for the inverse matrix, but really I need to know if the inverse exists. If I think of the formula for the inverse matrix, it's like 1 over the determinant of the matrix times some other matrix that's kind of a little goofy, right? To know if that really exists, I have to check the determinant of this matrix. But the determinant of this matrix should look familiar. What is the determinant of this matrix? Do we have a name for that? What? Wronskian, absolutely. The determinant of this guy would be the Wronskian. Okay. We also have another technique from linear algebra that will allow us to simplify this called Cramer's rule. So if you saw Cramer's rule, it's a way you can write out the formula to a linear system like this. What do? You take K1 prime. To write out just the solution for that piece, what I do is I take the determinant of the matrix, which in our case is the Wronskian, and the numerator I put another determinant that looks kind of like the denominator, except I replace the first row with the right-hand side. So I go like this instead, times x2 prime. Okay. Now that might be hard for me to remember. So what I'm going to do is I'm going to give that guy a name. It looks just like W, except the first column is different. I'm going to call that guy W1. Okay. It's going to be the Wronskian, except the first column is replaced by 0 on the right-hand side of the differential equation. And the reason it is that is because of Cramer's rule. It's just using Cramer's rule to solve this little linear system. Okay. I can do the same thing for K2 prime. And the only difference is the numerator, instead of replacing the first column, I replace the second column. Okay. All right, to summarize, this is really the important stuff here, right? Because you know what? Right from the get-go, right from the very start, once I find out complementary solution, I know what x1 is. I know what x2 is. So I can just use that knowledge of x1, x2 to go ahead and directly write down what W is, W1, W2. That's like your first little step in actually solving this. Calculate the Wronskian, calculate W1, calculate W2. And then when we saw that we can use those things to write expressions for K1 prime and K2 prime. K1 prime is just W1 over W. K2 prime is just W2 over W. Now, is that what I want? I want K1 prime. Is my assumption for XP have a K1 prime in it? Got a K1 in it, right? So how do I find K1? Anyway. And so you use these formulas to find K1 prime and K2 prime. Integrate to find K1 and K2. XP then becomes K1 x1, K2 x2, and the general solution is the complementary solution. That's a particular solution. Okay. So where did it come from? It came from this assumption, taking the derivatives, plugging it in, making another assumption, solving a linear system, all that kind of junk. How are we going to go through these problems step by step to find our solution? I will scroll to that as soon as people are done writing. Yep. That is the assumption that drives the bus, right? So whoever first came up with the technique, that is the assumption they made that led to good solutions. And we can show that we just need one solution, and then we can have all of them, right? We can show that if we just find one good solution, XP, then that the XC plus XP is the whole general solution. We can show that from linear algebra. How do we find that XP? By hook or by crook, right? So this technique works. Yep. All right, then we get 3 by 3 determinants, 4 by 4 determinants. Same process though. You just replace the first column, second column, third column, fourth column, whatever column with 0, 0, 0, 0, 0 function on the right-hand side of the differential equation. So it absolutely generalizes higher and higher and harder, right? Because the determinants get horrible as you go up. Okay. Good questions. Other questions? All right, let's get through one all the way here. Here is what I'm going to call my solution process. Okay. Step one, find the complementary solution. Once I do that, I will know what x1 and x2 are. From there, I calculate all the pieces I need, right? W, W1, W2. Use that to find my K1 prime and K2 prime. And then going to find K1 and K2. Use that to form XP and form X. So, go ahead and get started. Complementary solution, YC, is the solution of the associated homogeneous problem. So we start by solving x double prime plus x equals 0. That's where we start. All that. Auxiliary equation. Find the forms. So starting with x double prime plus x equals 0. What's the auxiliary equation we get from there? What are the ruts? That part should be bang, bang, bang. All right, there's x sub c, right? Now we can see this is one small part of this bigger problem now, right? That's why that homogeneous problem, you got to be able to put those up, solve those quickly. Auxiliary equation is r squared plus 1, my roots are plus or minus I, so I have my real part is 0, beta is 1. Throw it in my form, there's my complementary solution. Okay? Once I write that out, I can see what x1 and x2 are. I have c1 x1, so x1 must be cosine of t. x2 must be sine of t. Now I have the pieces I need to build all my w's here. So what is w, the Wronskian? It is x1, and then the derivative of x1. Derivative of cosine is negative sine. The other column is x2 times the derivative of x2. And now I calculate the determinant. I take this product, I'll get cosine squared of t, minus this product, negative sine squared of t. Negative and a negative is a positive. Cosine squared plus sine squared is 1. You got to be able to see that. If you're carrying around cosine squared plus sine squared through the whole problem, it will be a headache, right? So you got to make sure you see that simplification. What is W1? Well, I'm just replacing the first column with 0 and secant of t, the right-hand side of my differential equation. The second column is just the same as W. Oops. I have 0 minus sine of t times secant of t. Somebody simplify that for me. What's sine of t times secant t? Tangent of t. Right? Secant is 1 over cosine times sine, sine over cosine. So I have negative tangent of t. What's W2? Well, now I leave the first column like W, cosine of t, negative sine of t. Replace the second column with 0 and secant of t. Now I have the product of cosine times secant. What is cosine times secant? 1. So 1 minus 0 is 1. Now I can form K1 prime. That's just W1 over W. So I just get negative tangent of t. I form K2 prime. K2 prime is just W2 over W, just 1. But now I need to find K1 and K2. What do? I integrate both sides here, integrate both sides here. I will do K2. All right, what's K1? K1 I'll just give you here because we're running out short of time here. You would do it with a U substitution though, right? You write tangent is sine over cosine, let U equal cosine, work through the rest of the substitution. It's really not that bad of an integral. The result is going to be a natural log of cosine of t. You get that through the substitution. We can kind of check it by looking at it. If I took the derivative of that guy, I get 1 over cosine of t times the derivative of the inside function. That would kick out a negative sign. You'd have negative sine over cosine. Okay. Now I have K1 and K2. That tells me that XP is K1 formally here, K1 times X1, K2 X2. So this is natural log of the absolute value of cosine of t times X1, which is cosine of t, plus K2, which is t, times X2, which is sine of t. That's XP. What's our general solution? It's XC plus XP. It's C1 cosine of t, C2 sine of t, plus XP, natural log of the absolute value of cosine of t, t, sine of t. There's our solution. Okay. It's a long process, right? Once again, we got to understand where the values are coming from that general information. I do not expect to make an assumption. We need to be able to calculate W, W1, W2, form our K's and form our delta. Now, we're great, right?